Let's begin today with a simple but deep question. What exactly is mass? You've probably used weighing machines at home or at the doctor's clinic. But are they really measuring your mass? Mass is not just about how heavy something feels. It is actually the amount of matter a body contains. In physics, mass is a scalar quantity, which means it only has magnitude, not direction. And the standard unit we use to measure mass is the kilogram. Now here's something interesting. The mass of an object doesn't change just because you moved it from your room to your rooftop or even from Earth to the moon. That's because mass is constant for a body at rest and does not change with location or motion, at least under normal speeds. It's an intrinsic property, one that belongs to the body itself. You measure mass using a physical balance, and that balance stays accurate even if gravity changes, because gravity acts equally on both sides. But what if a body moves extremely fast, close to the speed of light, say, around 3 × 10 to the power 8 meters per second? Well, then we start seeing a noticeable increase in mass due to relativistic effects. But unless we are talking rockets or particles, for everyday motion, we treat mass as constant. Let's dive deeper into mass and understand its characteristics. Firstly, mass is intrinsic. That means it doesn't depend on where you are or how fast you're moving. It's like a fingerprint of the object's matter. Secondly, for everyday purposes, mass remains unchanged whether the body is stationary or moving, unless, again, we get close to light speed physics. Mass is typically measured using devices like a beam balance. And here's the catch. Unlike a spring balance which measures weight, a beam balance gives you the actual mass because it compares matter, not force. It's also important to remember that mass and weight are not the same. Just because you're lighter on the moon doesn't mean you've lost mass. It only means gravity is pulling on you less. In short, mass is constant, mass is scalar, and mass does not depend on gravity. Imagine a balance scale. No matter where you take it, the readings don't change because both sides are equally affected by gravity. That's the beauty of mass.
Now let's switch gears and talk about weight, something that does change with location. Weight is the force with which the Earth pulls a body towards its center. Unlike mass, weight is a vector quantity. It has both magnitude and direction, and that direction is always downward, toward the Earth. Think about dropping an apple. The force pulling it down is its weight. And what determines that force? It's the product of the object's mass and the acceleration due to gravity, which we denote as g. So the formula is W equals m into g. That's weight equals mass into acceleration due to gravity. For example, if you have a 5 kilogram object and we use g as 9.8 meters per second squared, then the weight would be 5 into 9.8, which is 49 newtons. So yes, your weight is measured in newtons, not in kilograms. Alright, let's talk units. The SI unit of weight is the newton, named after Sir Isaac Newton, of course. 1 newton is defined as the force needed to accelerate a 1 kilogram mass at 1 meter per second squared. Pretty neat, right? But there's also the CGS system, where we use the dyne. And here's a quick conversion tip. 1 newton equals 10 to the power 5 dynes. Weight, being a force, has a dimensional formula of mass 1, length 1, time minus 2. That's m1, L1, t minus 2. If you want to convert weight from newtons to dynes, just multiply by 10 to the power 5. So, a weight of 2 newtons is 2 into 10 to the power 5 dynes. That's 2 lacdynes. Now let's connect the dots. How are mass and weight related? They're connected by this fundamental formula. W equals m into g. So weight is directly proportional to mass. That means if you double the mass, the weight also doubles, assuming gravity is constant. But gravity isn't always the same. On Earth, g is approximately 9.8 meters per second squared. On the moon, it's only about 1.6. So while your mass stays the same, your weight drops drastically on the moon. That's why astronauts bounce around so easily up there. To put this in perspective, if something weighs 60 newtons on Earth, it would weigh only 10 newtons on the moon, but its mass remains unchanged. Let's solidify our understanding with a solved numerical example. Problem: what is the weight of a 10 kilogram object on Earth? Step 1. Use the formula W equals m into g. Step 2. Substituting values. M is 10 kilograms and g is 9.8 meters per second squared. Step 3. Multiply. 10 into 9.8 gives us 98 newtons. So the weight of this object is 98 newtons. Now for a twist, what if we took this same object to the moon, where g is about 1.6? The weight would be 10 into 1.6, which is 16 newtons. This clearly shows how weight varies with gravity, while mass remains the same. Let's quickly recap what we've learned today. Mass is the amount of matter in an object. It's a scalar quantity and remains unchanged regardless of where you are. Weight, on the other hand, is the force due to gravity acting on that mass. It is a vector, and it varies with the strength of gravity at different locations. The key equation linking them is W equals m into g. Weight equals mass into acceleration due to gravity. While mass is measured in kilograms, weight is measured in newtons or dynes depending on the system. And remember, if you ever go to the moon, you'll weigh a lot less, but you'll still be carrying the same mass of knowledge. I hope you now have a clear understanding of the difference between mass and weight, a concept that pops up everywhere from elevators to rocket launches. See you in the next session with another fascinating concept of physics.